Welcome back to your favorite engineering mechanics class, for which we are now continuing into our new topic, internal forces. So far you have learned how to calculate support reactions for rigid bodies, and you may think of those support reactions as actually external forces. And today my goal is to talk about internal forces for rigid bodies. So let's understand today what internal forces are. And to help you with that, my goals today are first to introduce internal forces to you. And while I will do that first with a 3D understanding, we will ultimately only look at these from a 2D perspective. That's already challenging enough, and we will have enough fun with that. And we will continue with 2D analyses, but we need to have a 3D understanding of the force system that we actually collapse into a 2D system so that we really understand what internal forces are and, for example, why they are named the way they are named. And that will directly lead us into the proper sign convention that we need to understand and always need to follow to clearly understand how these internal forces work in the 2D world and technically also in the 3D world, but again, that's beyond the scope of this class. Ultimately, we want to be able to really calculate internal forces at any point, but in today's lecture, as an introduction, we're going to do that at a very specific location only. And we do that along the axis of a beam, and today for simply supported beams, just because it's a nice introduction. Later on, our goal will be to not do it just for simply supported beams, but to do it for any type of rigid body and also anywhere along the rigid body. So with that said, let's go ahead and start the lecture, and let's first understand that these internal forces that we are talking about today are really forces that act inside structural members, right? So forces that act inside structural members. And effectively, that means that this is the force that keeps the rigid body together, or the structural member. So it's the force inside that keeps everything together. You may think of this as the glue that holds everything together inside a particular rigid beam. And to further look at that, let's take a look at this three-dimensional picture here of my, let's call it a tabletop. And so I need supports. Let's say I have a support here on the left side, and let's say that's a roller, and then one here on the right side. And let me first spend some time talking about something you have seen and used a lot before, and that is the reference fiber here. In fact, let's make clear that we understand that this thing here is called the reference fiber. Reference fiber. And so far, it's absolutely okay if you just have used it and you didn't care about what it was, but I will explain today to you why you need to understand the meaning of the reference fiber. So from now on, you need to have a clear understanding what the reference fiber does, and you will learn that it actually is related to the definition of the individual internal forces, but more on that later. For now, let's understand and remember that the reference fiber really indicates where the positive x-axis is pointing, and probably more important so, where the positive y-axis is pointing, and that is always opposite to the reference fiber. And you may think now, why do I need a reference fiber? I clearly understand that if I have a horizontal member here, that the x-axis is pointing to the right and the y-axis is pointing up. And that's absolutely correct. But what happens if you deal with a vertical member? Do you put the reference fiber on the left side or on the right side? Or what happens if you have a sloped member that is neither horizontal nor vertical? Then where do you put the positive, where do you put the negative side? So the reference fiber helps us to understand in which direction the y-axis is pointing relative to a local coordinate system that is defined by the axis, in this case the x-axis, of the beam. And you will see when I talk about the specific internal forces how important that is. But now to get to that point, what internal forces are, let's think about the fact that these internal forces are really the glue that keeps the thing together. And what do engineers do when they want to find forces? They pretend that the force is not there. So in the context of this table here, what I can do is I can just cut it, in this case, in 3 individual pieces. And let's just pretend I do it this way. And then when I separate them, what I did, I actually released forces that are inherent to the system when the rigid member is connected. So when this rigid member here is connected, and then you think of this line as the glue line, if you will, then you have internal forces that are connected from one piece to the other. To clarify that, let's call this here piece 1, this here piece 2, and then this here piece 3. And there is effectively some glue that holds them together, right? So this glue holds them together, but I'm an engineer and I want to know, hey, how strong does this glue have to be? And to figure that out, I just take it apart and then pretend, I took the force away from the glue. How much force do I need to bring it back into place? And to conceptualize that, let's just pretend for 1 second that we have a force here on the system, on the table. So let's say I have a force that acts exactly in the middle with, I don't know, let's say 10 Newton. It doesn't matter really right now. Maybe it's 1 Raphael, maybe it's 1 student. It doesn't really matter. But now you know from symmetry and things that we talked about before that, of course, each support reaction here has a resistance. And in this case, with 10 newtons on top of it, of course, we have 5 Newton pushing up here because it's symmetric. And then I also have 5 Newton on the other side. Okay, and now you can already guess where we're going. I took it already apart for you here in the pictures on the bottom. So let's bring down our reference fiber first, and let's see how the system looks after we cut it apart and what forces do we actually have to deal with. So in the middle piece, I have, of course, my 10 newtons that's pointing directly down in the center, 10 Newton here. And I have my support reactions, which are in this case 5 newtons on each side. But we don't care about the specific numbers here right now. Right now I just want to symbolically introduce to you how these forces work and what we just done. And what we have done is we actually created imbalanced systems. So we have 3 systems here, and in fact, to make that 100% clear, let me introduce the numbers. This was member 2 and this is part 3. And each of these elements are now separated. We cut through the glue and these systems are not in balance. So this one here is with an imbalance up with 5 newtons. This one is with an imbalance down 10 newtons, and we have an imbalance here. So the glue at this connection here really made sure that we somehow can transfer the 10 newton from the center to the support. And so far this has just been accepted as magically happening for us, but now we want to learn how that works. So the question we really need to ask ourselves is, what do we need to do at this surface here and this surface to bring the system back into equilibrium? And we can do this piecewise. We can first bring this back into equilibrium, then bring this one back into equilibrium, and then this one, or in any random order really. So you may already understand why I'm using a 3-dimensional description on top of this 2D dashed fiber or the 2D system that I used here and here, because we want to represent this glue here. The glue is really what keeps this surface together that would not be available to us if I would just look at an x-y coordinate system. But we need to understand what's acting on this surface here, which is the glue line. So let me actually add these 2 diagonals here so that we understand better that the force is actually acting on that surface that we will now introduce to bring our systems back into equilibrium. And of course I can do this for all of the individual surfaces that are seen here, but please understand that they're also available on the surfaces that are away from our view right now. But to show these a little bit better, let me actually draw some faint dashed lines here in the background, because those are the surfaces opposite to the ones that we can see here. And those, of course, have to also carry some forces to transmit the loads between one side of the glue to the other side of the glue. So that's what you see here now with the dashed line. Okay, so now we can ask ourselves, how do I bring this piece, element number 1, back into equilibrium so that it doesn't fall down here on the glued line, because it didn't fall down up here. I just virtually cut the system and pretend that I'm analyzing the glue now. So what do I have to do? Of course, you already see that it's in imbalance in the vertical direction. Therefore, I need to somehow bring a force into the system that pushes against the 5. I don't really care about the values here, but I care that I need to balance the vertical direction. So I actually need a force that is pointing down here. Now, what is this force doing? It's pointing down, but it's also parallel to this surface, if you will. It's not perpendicular, it's parallel to the surface. And so you may already know what these forces are called, but think about what a force is that is parallel to a surface. Exactly, it's a shear force, right? So engineers call that a shear force, but the layman calls it a shear force too, actually, because if you think about the scissors in your home, what do they really do? They have two surfaces, just like this glue and this surface here, that shear parallel to each other. That's why we also call scissors shears, right? But now we have this imbalance, or we can potentially use this force to bring the system in the vertical direction in balance. But the trained engineering eye already sees that these forces, even if they have the same value, 5 Newton and 5 Newton, they would cause this system or this rigid body or the part of the body to rotate. In this case, it would rotate clockwise. So we need to do something against that. We need to bring in a force or some system that prevents rotation. And of course, you already know how that works. You know that you can use a moment, because a moment is the tendency to rotate. And so this rotation that the 5 and the 5 here would cause clockwise can be resisted by this tendency to rotate in the opposite direction. So this here would be the moment. And now you may think, this is in equilibrium, and seemingly that is correct. But we need to understand another thing, that we could in a 2D system have yet another type of force, which in this case actually happens to be on the right side. It's here where the pin is, because the pin also resists forces in the horizontal direction. So we need for the glue to be able to also transfer horizontal forces from element 1 to element 2, right? So there needs to be a force here that actually acts in that direction. And to no surprise, we can draw that with a force that is actually acting in this direction, which now is perfectly perpendicular to the shear force and to the surface that is acting there. And because this is actually perpendicular to the surface with the green diagonals, we call that, exactly right, we call that a normal force, right? So this is a normal force because it acts normal on the surface. And once again, you see why I'm using a three-dimensional picture to describe something that we will analyze in 2D, because we would not understand why this is called a normal force or a shear force if we did not have this surface available to us. This surface really gives rise to the name normal force and shear force. But now, in a two-dimensional sense, if you look at this picture without these diagonal lines, these three entities, the shear force, the normal force, and the bending moment, are capable to keep this glue and the system in equilibrium. Of course, in this case, the normal force here is 0, right? Because there's no external force acting here. But we still need the glue to be able to transform that. All right, now we have one system in equilibrium. The next easier one is probably the part 3 here. So the system 3, let's put that into equilibrium. And yes, you guessed it, we of course need a shear force, a normal force, and a bending moment as well. So let's introduce those forces too. We need a vertical resistance in the glue. We need a horizontal resistance in the glue. Again, these two are perpendicular to each other. And we need a moment that is strange to see in this case, but we need something that prevents bending as well. And right now, I'm not really concerned about the direction. Of course, we kind of intuitively feel that the force here should be pointing downwards. The normal force, as you will see in a second, always points away from the surface. And then the moment also has a special definition usually, but we will see that later. It really rotates clockwise in this element 3, and you will understand why this is a different rotation than this one here. Of course, I could have also put the arrowhead here on the bottom side, but there's a specific reason that we will talk about in just a little bit why this is pointing or rotating counterclockwise, where this one is turning clockwise. And similarly here, this is pointing to the left and this is pointing to the right. And the reason for that really is because we're trying to pull away from the surface and pull away from the surface. All right, so now with these three forces, we also have element 3 in equilibrium. So now we have to put element 2 in equilibrium, because while this is not falling down or rotating, and this one is not falling down or rotating, this one can technically still fall down with 10 newtons. So we have to balance this. And one important thing to note is if I put the first surface into equilibrium, let's say for the vertical forces, then yeah, you may think that now this could be in equilibrium because I have something pointing up and something pointing down. But notice once again that these two forces actually rotate the system. And even if I bring in a moment here on this side now, it could still rotate the system. So what do I have to do really? I, of course, have to bring in a force on the other side that actually can prevent that rotation from happening. So I would end up with something here. And to keep that in equilibrium, we have to point upwards as well. Now, the next easier one to deal with is the horizontal force or the normal force, which has to once again pull away from the surface. So I'm drawing them in these directions. And keep in mind they are perpendicular to each other. And notice a very important thing here. This force at the glue can balance this force at the other end of the glue. This normal force applies a force to this glue that is opposite to the force here that is applied to this glue, if you will. And so these cuts here, the space in between is actually in equilibrium if you want to think about it this way, because this force is pushing on the cut and this force is pushing in the opposite direction on the cut. And so what I'm trying to tell you is that it doesn't matter if you only look at this system here, only number 1, or if you look at 2 and 3 together, these forces, the normal force here, comes out to be the same as it would come out here on this side. So you can think, of course, of this system being 1. So forget about the cut that we made here. This system together would be the same as this one at this cut here. So therefore you understand that this is not really in equilibrium yet, because on the left side to it you have a bending moment that is also presented to the cut, and on the other side as well from element number 3. So we need to balance this rotation and we need to balance this rotation. In other words, I need something that resists bending here in the glue, and I need something that resists bending there. Now the question is, in which direction should they rotate? And the answer is already available here. So for element 1, we have an arrow that actually rotates counterclockwise. So to balance this counterclockwise rotation, this here has to rotate in which direction? Exactly clockwise. And if you look at the other side, you can argue two ways now. We don't know if this is rotating clockwise or counterclockwise, but you can say, hey, there's a rotation in element 3 that actually rotates clockwise, therefore this needs to be counterclockwise. Likewise, you could use the argument that element 2 has to be in balance in total, and if this is rotating clockwise, then this one here has to be counterclockwise. So that brings up or concludes the important point that the left side has to always balance the right side, for example. Or another way to look at this, if I look at element 3, I can say that element 3 here is in balance now, just with the same values as element 1 plus 2 would be at this glue line here as well. So everything to the right is the same as everything together on the left. And that is an important concept to understand. So now you know that we have always on these surfaces 3 forces, the shear force, the normal force, and the moment, and that they always have to be in balance with the other side, with the opposite side. Otherwise, the system would not be in equilibrium, and if the system would not be in equilibrium, then the glue would not hold it statically together, right? So this glue line here makes sure that element 1 and element 2 are together in equilibrium. And that equilibrium is just shown symbolically here. So the direction of these arrows is not how you will see them later on. So please do not get confused when you study this in the context of this picture here. This picture just tried to explain this conceptually, that you have to push in one direction and keep that in balance and rotate it into balance and so on and so forth. But we will later have a precise definition of when an arrow has to point up and when it has to point down. This may not be consistent with what you see here, but this gets the point across.